Welcome back to your third to last lecture. This is Physics 360, Week 13, Day 1, scheduled for release on April 14th. Today we will be discussing the vibrations of a circular membrane and the steady state temperature in a sphere. There are two assignments due today. One of those is the daily homework that was assigned last Friday. The other is periodic homework 6. If you plan to use a late pass, please let me know via email. On Friday, the daily homework for today is due, which is just two fairly short, fairly simple problems. Section 6, number 1, Part A only, and Section 7, number 1. We are covering Sections 6 and 7 out of Chapter 13 today. Test 3 opens this Friday and will be due the following Friday. I'll be sending you an email in a couple of days about the content that will be on that test. And I just want you to know right now that the very beginning of Chapter 13, roughly the first lecture or so of Chapter 13, is fair game for this test. Next week, Tuesday, April 21st, we do not have lecture. This was the day originally scheduled for Epic Expo, and I'm leaving this lecture canceled because Epic Expo may still be happening in some digital format, and because I don't want to mess with the syllabus schedule this late in the game. However, even though there will be no lecture posted April 21st and no daily homework due on that day, your second draft of your project is due that day to me via email. And the last periodic homework is shown at the bottom of the screen in red, periodic homework 7 that covers Chapter 13. The problems are all listed there. There are 9 of them, and you can skip any one problem, or you can do all 9 and have the last one count for extra credit. So on to today's material, and we're going to start off talking about the vibrations of a circular membrane. Now, since we are talking about vibrations, whatever function we find is going to have to satisfy the wave equation. And we're going to define our function, the displacement z of this circular membrane, as a function of the location on the plate and time. But since we have a circular membrane, using x and y for our location on the membrane is probably not the best idea. So instead of x, y, we are actually going to use r and theta, polar coordinates. So once all is said and done, we are going to have z as a function of r, theta, and t, and z must satisfy the wave equation as follows. The Laplacian of z equals 1 over v squared times the double partial derivative of z with respect to time. As we have with every other partial differential equation we've covered this chapter, we are going to start by assuming a separable solution, and we will start off by separating the time and spatial components of z as follows. The function capital F will be a function of r and theta and will contain all the spatial information, and the function capital T is going to have all of the time information. So we're going to do what we've always done at this point in the process. We are going to plug this in to the wave equation. We're going to divide by the overall function, that is F times T, and then we are going to rearrange. For the spatial part of this displacement function z, we get exactly what we got before. We are going to get the Helmholtz equation here, the Laplacian of f plus kappa squared, where kappa squared is our separation constant, times f equals 0. And this is going to yield the exact same results from section 5, where we split f into the r and theta components separately, which had the solutions that r was a Bessel function and theta was sines and cosines. The sines and cosines are of n theta, where n is an integer. The time portion of the, let me label a couple things more here real quick. This is the Helmholtz equation. And I want to add up above that we chose a separation constant of kappa squared. So now on to the time portion of the equation. Here we obtain the equation that the double derivative of t with respect to time plus kappa squared v squared times t equals 0, which has solutions of, again, sines and cosines, where our argument of our sines and cosines is going to give us k vt, or kappa vt, rather than just kappa. So far, everything seems fairly similar to what we've done before, and now we're actually going to bring in the aspects of our particular problem. So let's discuss exactly which circular membrane we're talking about. I had a demo planned for today that would have involved bringing in the Chladni plates, and if we use the Chladni plates as our example problem, we would have a very different structure to the rest of this problem than we're going to have, because we're going to assume our circular membrane is something like a drum head, which is fixed to a rigid frame around the circumference. And a drum head is fixed all the way around the circumference. So that means that the displacement along the perimeter of this circular membrane has to be 0. So now we are going to define a new quantity. We are going to let k equal kappa times a. And like before, these are going to be the zeros of the Bessel function. So to be very clear here, we might have multiple orders of Bessel functions, and each Bessel function has multiple zeros. So we're going to adopt the notation that k sub mn is the mth zero of j sub n. And with all of these in place, we can now start to write down what our function z might look like. So for our radial portion of z, we have the nth order Bessel function of argument kr over a, so that when we plug in r equals a, the argument of that Bessel function is just k, the zeros of that Bessel function. For the theta part, we have sines and cosines of n theta, and for the time portion, we have sines and cosines of kvt over a. One of the things we could do here to proceed is, like we did for the one-dimensional string, we could specify the initial conditions of this membrane. Maybe some initial velocity function representing an impulse delivered to this drum head at time t equals 0, or we could specify the displacement at t equals 0 and release our system from rest at that displacement. To do this, we would follow a similar process to the very end of section 5, the part that was not covered in the video. But this is a fairly complicated problem, and I want to do something different this time around. Let's study instead the normal modes and vibrations of this membrane. So for a 1D string, we have our mode number given by n. And the frequencies related to these are given by a very simple formula, that the frequency equals the mode number times the speed at which a wave propagates on that string, divided by 2 times the length of the string. But here, we have a two-dimensional circular membrane. And here, the frequencies of our normal modes are going to equal omega divided by 2 pi, where we know what omega is because that's what appears in the time portion of our overall displacement function. So that ends up the frequencies equaling kv over 2 pi a. And we have very many values of k, because kmn is the mth zero of j sub n. That means each k value will lead you to a different fundamental frequency. So we can write this as the fundamental frequency given by m and n, the mth zero of j sub n, is equal to k mn times v divided by 2 pi a. So we've found the fundamental frequencies associated with the vibrations of this circular membrane. So now what we want to do a little bit is to start to think about what do these different vibrational modes look like. So we could have various different values of m and various different values of n here. So let's kind of make a table up here. And let's remind ourselves of the form of our values for z down here in the lower left corner. Where for now we're using just the cosine parts of n, or the theta component and the time component, just to simplify our diagrams that we're going to make here. So when n equals 0, cosine of 0 is just equal to 1. So in this first box up here, we can rewrite our expression for z as follows. We will have j naught of k10 times r times the cosine of k10 times vt. So there's no theta dependence here whatsoever. And it will turn out that this arrangement gives us an entire drumhead that is all vibrating as one single whole. So I'm going to put a plus here to show that this drumhead, or a plus slash minus, to show that this drumhead oscillates up and down the entire thing all at once. So what does it mean then if we increase m from 1 to 2? Well, m is which zero of our Bessel function we have. So if m is now 2, then the zero corresponding to the very edge of this circular membrane is now the second zero of our Bessel function. So our formula would still look fairly similar. J naught of k sub 20 times r times the cosine of k 20 times t. And in terms of the circular membrane, that means that at the edge of this membrane, there will be the second zero of the Bessel function, which means somewhere partway out to A, there is the first zero of the Bessel function. So we'll have two distinct regions here, both oscillating up and down, but in opposition to each other. So while this inner circle here is at its maximum height, this outer circle here is at its minimum height, or a negative displacement. If we follow this process along for m equals 3, we would get everything is the same, but with k 3 sub 0 for each of our k values. Which means that the zero that corresponds to the very edge of this circular membrane will be the third zero of this Bessel function. So we'll have kind of three concentric regions here. And if the middle region is at its maximum positive displacement, the next one out is at its maximum negative displacement, and the outer region is at its maximum positive displacement as well. So now let's go down to n equals 1. Now our cosine of n theta here, term here, does not entirely vanish. So we are going to have some theta dependence. So let's write out our function for z. We now have the first order Bessel function, and it will be k sub 1, 1 times r. And now we have a cosine of theta term, in addition to the cosine of kvt term at the end. So, when we look at how this affects our drumhead, k11 is the first zero of the first order Bessel function, which means the zero that corresponds to the very edge of this circular membrane is the first zero that we will encounter. The difference here is this cosine of theta term. So cosine of theta will be 0 when theta equals 0 degrees, and theta equals 180 degrees. So this line right here, horizontally across the plate, with theta equals 0 taken to be over here on this side, will be a node. There will be no vibrations happening along this line. So one side of this line will vibrate one way, and the other side of the line will vibrate the other. So while the top half of the plate is at its maximum positive displacement, the bottom half of the plate is at its maximum negative displacement. To continue this process along, n equals 1, m equals 2 gives us still j sub 1, but this time of k 21 times r, still with the cosine theta and still with the cosine of kvt. So this circular membrane that we could look at, k sub 21 is the second zero of the first order Bessel function, so the first zero must happen somewhere between the center and the edge at r equals a. But we still have this cosine of theta term, which still creates a nodal line here. All of these dark lines that I've drawn here are all nodes, where the amplitude of the oscillations at those locations is 0. So here, we would have, again, different sections vibrating in different ways. While the sections labeled plus are at their maximum positive displacement, the sections labeled minus are at their maximum negative displacement. So we could then continue this on. And I'm going to jump down to m equals 1, n equals 2 for now, down here in the corner. And since n equals 2, our Bessel function will be the second order Bessel function. And that's k sub mn, so k sub 1, 2, the first zero of the second order Bessel function. And this time we have cosine of 2 theta, since n is now 2, along with our usual cosine of kvt term. So in terms of how the membrane looks, we have to think about the zeros of cosine of 2 theta. Well, those zeros occur at theta equals 0, theta equals 90 degrees, theta equals 180 degrees, theta equals 270 degrees. So that means I've confused my sines and cosines. Well, poop. You can either just pretend all of these cosine of thetas that I've been writing are sine of thetas, or we can pretend that theta equals 0 is actually down here at the bottom instead. My apologies, but the general shapes of these different vibrating regions are still the same if rotated 90 degrees from what they should be. So we will have a membrane that oscillates like this. So we can continue this along. I'm not going to actually redraw or write out any more of the equations, but just to show you what some other ones of these might look like. Here, where m equals 3 and n equals 2, we will have 3 nodal circles and a split along the line where cosine of theta equals 0, where each of these sections will alternate which one's at a maximum positive displacement and a maximum negative displacement. Or m equals 2, n equals 2 will be a combination of what you get from m equals 2, which is 2 concentric circles of nodal lines, but this time split every 90 degrees. And just like before, each section will be doing the opposite of the other sections that it is touching. And just for completeness sake, this last one here will look a lot like this, with the positive and negative referring to exactly what they were referred to before. So one of your periodic homework problems is actually to go through this same process of finding the normal modes and the normal frequencies, but for a rectangular membrane instead. Now I want to talk about the steady-state temperature distribution in a sphere. So since we're looking at the steady-state temperature, we are going to be looking for solutions to Laplace's equation. And since we're dealing with a sphere, we need those solutions in spherical coordinates. And setting up the separation of variables here is certainly no trivial task. So first, let's write out what the Laplacian looks like in spherical coordinates. One over r squared times the partial derivative with respect to r of r squared times del u del r is the first term, plus 1 over r squared sine theta, del by del theta of sine theta del u by del theta is our second term. And our third term is 1 over r squared sine squared theta, del squared u del phi squared, all equals 0. And just a reminder, especially for the mathematicians in the class, that I'm using the physics convention for spherical coordinates, where theta is the angle from the z-axis. So we're going to do what we've done before and assume a separable solution. R of r, theta of theta, phi of phi. And we are going to, as we have before, substitute this into Laplace's equation and divide by the overall function, r theta phi, but we're also going to multiply by r squared for a reason we'll see in just a second here. And we obtain the following equation when we do that. So hopefully you can see at least a little bit why I multiplied by r squared. We had r squared terms here in our original theta term right here, a 1 over r squared, and a 1 over r squared in our phi term as well. So in order to get the key feature of a separable solution, namely that one part of our equation depends on r and another part of our equation does not depend on r, we needed to multiply by r squared. So we still haven't completely separated our variables here, but we can if we multiply everything by sine squared of theta. So if we multiply everything by sine squared of theta, then this last term here will be only in terms of phi. So doing that and rewriting our solution, we obtain the following. And now we can say that this last term here is only in terms of phi. So we're going to pick ourselves a separation constant here. So this term that I've highlighted in yellow must be equal to a constant. And we are going to choose a negative separation constant of m squared because phi and theta are both periodic. They have to give you the same value for 0 as they give you for 2 pi. So to do this, that means m is going to need to be an integer, and this will give us solutions for phi of sines and cosines of m theta. Sorry, sines and cosines of m phi. So now we can use this fact that the last term is equal to negative m squared to rewrite our equation that we had up here in gray before we multiplied by the sine squared of theta. So now we can do kind of the next step of our separation of variables constant and define another separation constant. And we can do this by noting that this first term here is a function of only r, and that everything else contains no r's at all. So that means each of these two terms must be equal to a constant. So I'm going to take the r part of our solution over here, and we know that 1 over r times d by dr of the quantity r squared times dr by d little r has to equal a constant, and we are going to call that separation constant k. Which means the other piece of our equation right here that I am mousing over in blue right now also has to be equal to that same separation constant, but negative. And then we can rewrite this blue equation I've just written in a slightly different way. And we may not have done this problem, but from problem 10.2 in chapter 12, this is precisely the equation for the associated Legendre functions with k equals L times L plus 1, where L is always an integer. So we never really defined the associated Legendre functions. We skipped that section, so I just want to let you know what the associated Legendre functions are. And those are defined as p sub L with a superscript m of x gives you the quantity 1 minus x squared to the power of m over 2 times the mth order derivative with respect to x of PL of x, our regular Legendre polynomial. So do note when you're looking at the associated Legendre functions that if m equals 0, PLM just equals P sub L. And this is easily verified by just inspection of that formula. So this means we now know the solutions for our theta component of our equation here. So theta is going to be the associated Legendre functions, p sub L superscript m of cosine of theta. So cosine of theta has taken the place of x then. So now we can do a little more with the r portion of this. So when we have k equals L times L plus 1 with L as an integer, r, capital R as a function of little r, has two following possibilities, r to the L and r to the negative L minus 1. And we're going to discard one of these in this problem for a very specific reason that I'm going to kind of write over here in this little bit of space that I have left over in red. We are asking in this problem about the interior of the sphere. So we need to include r equals 0 as part of our solution. And we assume that the interior of the sphere is not at infinite temperature. And when you plug in r equals 0, or when you let r go to 0, one of these functions explodes, and we're going to have to discard that function. R to the negative L minus 1 evaluated at r equals 0 gives infinity, or an undefined solution if you're more formal about things than physicists are. But I'm a physicist, so I'm just going to say it's infinity. And we don't want infinite temperatures, so we are going to have to discard the r to the negative L minus 1 solution. So now we have generally our basis functions of the steady state temperature in a sphere. R to the L times the p sub L superscript m of cosine of theta, that is the associated Legendre function, times either the sine of m phi times the cosine of m phi. And there's a special function that has its own special name that is buried in part of this equation that I want to draw your attention to, and that is just the angular components of this solution, the parts that don't depend on r. And the associated Legendre function times the sines and cosines of m phi, these are called the spherical harmonics. And they are given the variable capital Y, subscript L, superscript M, and they are a function of both theta and phi. So all of this was very general. Everything we've done on this slide would be true for any sphere of which we want to know the steady state temperature on the interior of the sphere. To do anything specific, we would need to know some boundary conditions. So what temperatures is the sphere being held at? And that's the example we're going to do next. So we're going to let the temperature be held at 100 degrees on the upper half of the sphere and 0 degrees on the lower half of the sphere. So drawing a picture, that might look something like the following. So here's our sphere, and the entire top surface up here, we are going to hold at 100 degrees, and the entire bottom surface down here in blue, we are going to hold at 0 degrees. And just a quick reminder, this right here is the z-axis. So if we are referring to this point on the surface of the sphere, this angle I am taking to be theta because I am a physicist and I just want you to be aware. So we do expect our solution to depend on theta, but we have no reason to expect our solution to depend on phi. If we rotate this sphere through some angle phi, it does not change the temperature distribution at all. So we're expecting a solution that is independent of phi. So this means we're going to have to use, for the phi portion of our solution, cosine of m phi with m equals 0. So that is cosine of m phi equals 1. And note what I mentioned on the previous slide as well, that with m equals 0, our associated Legendre functions just become our Legendre polynomials. So this gives us our basis functions that we can write as a linear combination to obtain our overall functions. Our basis function u sub L is going to be equal to r to the L times p sub L of cosine of theta times cosine of 0 phi, which is just equal to 1. So we'll leave it off entirely. So this means we can write our overall solution, u, as a linear superposition over all possible values of L, from L equals 0 to infinity, with a coefficient c sub L, and then the rest is the same, r to the L power, times the Lth order Legendre polynomial with an argument of cosine of theta. Now we need to start worrying about our boundary conditions. And the boundary conditions here are most relevant at r equals a, the radius of this sphere. So the temperature evaluated at r equals a simplifies our expression in the following way. We still have the sum from L equals 0 to infinity. We still have c sub L. We still have r to the L. Really everything is the same, with the exception that we are plugging in the value of a for r. And we know this has to equal 100 degrees on the top half of the sphere or 0 degrees on the bottom half of the sphere. So let's think about how we can write this down mathematically. Well, we could write this down in terms of theta, again, the angle from the z-axis. The upper half of the sphere is when theta is between 0 and pi over 2. And the lower half of the sphere is when theta is between pi over 2 and pi. But we can be clever and write this in a slightly different way, because the argument of our Legendre polynomials is the cosine of theta, not just theta. So we might want to write our limits in terms of the cosine of theta. And when theta is between 0 and pi over 2, that means cosine of theta is positive. So the cosine of theta between 0 and 1 means we're in the top half of the sphere. And the cosine of theta between negative 1 and 0 means we're in the bottom half of the sphere. And this will help us because if we think back to our PL of x functions, we now have this defined in terms of x being greater than or less than some quantity, where our x that we have is just replaced by a cosine theta now. So let's rewrite this equation a little bit in a way that will actually help us see what's going on. So I've just replaced here using x equals cosine theta. So I've just written this in terms of x instead of cosine theta, where the cosine theta in the Legendre polynomial has become an x, and that is the only change. And we want this evaluated at r equals a to be equal to 100 times the function f of x, where f of x is defined as follows up here. F of x is just going to be equal to 0 when x is negative, and 1 when x is positive. I've also added the limits of 1 and negative 1 here because we do know that x is really cosine theta, so x cannot possibly have a value outside of 1 and negative 1. And now what we're going to do here is we are going to expand this function, f of x, in a series of Legendre polynomials. You can look at Chapter 12, Section 9 if you want more detail, or you can think back to some of the problems we did about writing polynomials in terms of Legendre polynomials. That won't work for this particular problem because we're not modeling a polynomial, we're modeling a piecewise function, but it's a similar idea. So when we do this, we get the following. Including the first four non-zero terms, we have half of the 0th order Legendre polynomial plus 3/4 times the first order minus 7/16 times the third order plus 11/32 times the fifth order. So the coefficients here in our Legendre polynomial expansion of f of x are related to our coefficients c sub l in our actual function we're trying to find here. So each coefficient c sub l is equal to the coefficients from the Legendre polynomial expansion times 100 over a to the l. Which means we can now write the final answer for this problem, and that is u equals 100 times a slightly modified version of our Legendre polynomial expansion from above, where we have 1/2 times the 0th order Legendre polynomial of cosine of theta, plugging back in for x, plus 3/4 times r over a times the first order Legendre polynomial as a function of cosine of theta, minus 7/16 times quantity r over a cubed times the third order Legendre polynomial of cosine of theta, plus 11/32 times r over a quantity to the fifth power times the fifth order Legendre polynomial of cosine of theta, and this is an infinite series, so it does keep going. But this is our final answer to this specific problem. Now remember, everything from the previous slide was general. It will work for any steady state temperature in a sphere problem. But this function that I've written now and everything on this slide is all about this particular problem with the boundary conditions and surface temperatures exactly as given here. That is everything for today. There are now only 2 lectures remaining in this course, one more from Chapter 13 and one about numerical methods. And, well, we're getting pretty close to the end here. So good luck, thank you for watching, and have a good day.